We're going to be looking at gravitational potential energy and kinetic energy and the exchange between these energies. Gravitational potential energy is the energy stored by an object due to its position in a gravitational field. And gravitational potential energy is calculated by the mass multiplied by acceleration due to gravity times by delta H, or the height the object moves through in this gravitational field. We're now going to derive this equation. And so the object has gained height, so we say it's gained gravitational potential energy. So work has been done on the object to move it against the force of gravity. So the definition of work done is equal to the force times the distance moved in the direction of the force. Our force is the weight of the object, and S is the distance moved in the direction of the weight. So weight acts along the vertical direction, so S equals our delta H. So if we substitute all this into our equation for gain in GPE, we get the force, which is the weight, multiplied by the distance moved in the direction of weight, which is our delta H. It's important to note that this equation deals with changes in gravitational potential energy, not absolute values, because the height is measured relative to a surface. So that could be relative to the surface of a table or relative to the ground, and so it's just dealing with changes in GPE. It's also important to note that in this equation, our G, acceleration due to gravity, or gravitational field strength, is only constant when it's near the Earth's surface. So you can use the value of G equals 9.8 Newton per kg or 9.8 meters per second squared only when we're looking at changes that are close to the Earth's surface. Kinetic energy is the energy associated with the motion, the movement of an object, and it is calculated by half times the mass of the object times by the velocity squared. These values need to be in SI units so that the units of energy will be in joules. And we're now going to go through the derivation of the kinetic energy equation. So we can say an object has kinetic energy, and that is equal to the work done to move that object from rest, where it had no kinetic energy, to velocity v. So to move the object, we need to apply a force on it. So work is done on it, and that is equal to the gain in kinetic energy. So from the definition of work done, we say it's equal to the force times the distance moved in the direction of the force. So our kinetic energy is equal to the F times S. Because the object has accelerated from an initial velocity of 0 to a final velocity v, then we can say this force is equal to mass times acceleration. So if we substitute that for F into the equation for kinetic energy, we can say kinetic energy equals ma times S. We're assuming this is a constant force, then the acceleration is constant, so we can use the Suvat equation, v squared will equal u squared plus 2as. Because u is 0, you can see then that as will equal v squared divided by 2. And if we substitute for AS into this equation for kinetic energy, we're going to get M times V squared divided by 2. That is a half mv squared, our equation for kinetic energy. We're now going to look at an energy transformation between gravitational potential energy and kinetic energy. So here we have a ball that is projected upwards. So the energy transformation is from kinetic energy to gravitational potential energy. That is because the ball is moving upwards, it's decelerating, it's losing velocity, and so it's losing kinetic energy. But as the ball is moving upward, it's gaining height. If it's gaining height, it's gaining gravitational potential energy. So KE is converting to GPE. When the object is moving downwards, the energy conversion is gravitational potential energy to kinetic energy. And that is because as it's moving downwards, it's losing height. And so it's losing gravitational potential energy. But as the ball is moving downwards, it's gaining velocity because it's accelerating downwards due to gravity. So it's gaining kinetic energy. So you can see it's a transformation from gravitational potential energy to kinetic energy. I'm now going to do a calculation involving energy transformation. So we have a man who is initially at the top of Mount Everest. So has an initial energy is in the form of gravitational potential energy. So we can say his initial GPE is equal to his mass, which is 60 kg, times the gravitational field strength, or the acceleration due to gravity, times the height. So the height, so relative to the ground, is 8.85 kilometers, which is, to get kilometers into meters, we have to times that by 1,000. So that gives us initial kinetic energy of 5.2 megajoules, mega being 10 to the 6. If the man is now suicidal and drops himself off the cliff, we can then say his GPE energy is converting into kinetic energy. So we're going to try and determine the speed at which the man hits the ground. So we can say his initial GPE will equal the final KE. So at the ground, the man will have no GPE. So all the GPE has converted into kinetic energy. So kinetic energy is a half mv squared. And that must equal our initial gravitational potential energy. So that is 5.2 megajoules. So if we now substitute the mass for 60 kgs and rearrange, we can get the velocity at which the man hits the ground. So that is going to equal the square root of 2 multiplied by the kinetic energy divided by the mass. Substituting the values, we'll get a speed of 416 meters per second. We have made one assumption in that there's no energy loss. So we've assumed 100% efficiency in the transformation of GPE to KE.